Hey, grade 12. So today we're going to combine rate laws, stoichiometry, mechanisms. We're going to kind of take everything and just put it all together here. Mostly a little bit of theory here, but we can kind of see how all of these things we've been talking about, mechanisms, rate laws, coordinate diagrams, everything is all interconnected. So here we go. We've seen that for most reactions, the rate laws, the rate constant, and the mechanism, we can only figure these things out experimentally. Now, if we have a single step reaction, we haven't talked about those in a while, or an elementary reaction, the order of the reactant is equal to the order of each reactant is equal to the coefficient in the reaction. So we don't actually have to do the trial 1, trial 2, initial rates method. We can actually just take the coefficients and put them right into our rate law. And that's only for single step reactions, and you'll always be told if a reaction is an elementary or single step reaction. So here's an example. If we have this elementary reaction, A and B make C and D, the rate law would look like this. And what I'm trying to show you is that these coefficients become your powers in the rate law. They become the order of each thing because since it's only one step, each reactant has to affect the rate, and it'll affect the rate by how many of them are needed for the reaction to happen. So that's what I said here. A and B are molar coefficients of the elementary reaction. So this only works for simple one-step reactions, and that's why we left it to the end, because it's the easy part. So here's an example. This is the reaction that causes, or the results in smog is ozone and reacting with NO, making NO2 and O2. If we want to find the rate law, if this is a one-step reaction, the coefficients are simply the order of each reactant. So our rate law is just that, because you would see that there's a coefficient of 1 here and a coefficient of 1 here. So the powers are 1s. If one of those coefficients had been a 2, you just put a 2 as a power. And that's the easiest rate law we can get. And that's only for elementary reactions. So think elementary, think easy. So think easy rate laws. Now, we can also talk about mechanisms, and I kind of alluded to this earlier. If we're talking about rate laws, remember that the only step that affects the rate in a mechanism is your rate determining step, or your slowest step. So since we have mechanisms, we will know the simplest step, or the slowest step, and all of those steps in the mechanism are going to be simple or elementary reactions, because that's the whole point. You've broken them down into single steps. So the rate law for these reactions will correspond to the stoichiometry of the RDS, or the rate determining step. Any reactants that are zero order must not be in the RDS. Anything that has zero effect on the rate must not be in the slow step. It must be in a fast step. So here's an example. Here's a mechanism. If we're looking at those 3 steps, the step that determines our rate is this step. Everything else doesn't matter because they're faster. We can only ever go as fast as our slowest step. So our rate law, like if I wanted to write the rate law for this reaction, it would look something like this. Rate equals K times M to some power times N to some power. We wouldn't know those powers, and we'd have to go and do a bunch of trials and stuff. But since we know this mechanism, N does not appear in our slow step. So that means it has 0 effect on the rate. So it's 0 order. So our rate law is going to look like this. Rate equals K times the concentration of M. But since this is a mechanism, and these are going to be elementary steps, then now I know that that coefficient is actually my power and my order of M. So there's our rate law. And if I tripled the amount of M, triple squared is 9. 9 times faster. The effect of doubling N? None, because it's not in your rate law. Now, we can, and I'm not going to ask you to do this, but to understand why mechanisms and rate laws are kind of important, is the rate laws actually give us a clue into what the mechanism of a reaction may be. So I'll give you an example. We can find the rate law doing experiments, just like we did with the initial rates method, trial 1, trial 2, blah, blah, blah. So let's say we have this reaction. We want to figure out what the mechanism might be. We know that it's likely not to occur in one step. We want to figure out what those steps might be. So we're going to do our data, our trials, and all this stuff, and we're going to figure out our rate law. And we get this as our rate law. So when I see this, I know right away that this reaction is not one step, because that is not the order of NO2. NO2 is actually only first order. So there must be more than one step in this mechanism. So a possible mechanism, though, will have the stoichiometry will have coefficients of 1 for these two reactants in your rate determining step. And then those products would have to reflect that. So step 1 could be this. This would be your slowest step. Notice you have a 1 here and a 1 here. Well, that's where those orders come from. So that means that Cl has to be an intermediate because it's not appearing in the overall reaction. So a next step could be this. And that, if we added those together, we get that overall reaction. So this is a possible mechanism for that reaction. Now again, we can't find the definite mechanism. We can't see this stuff happening. It happens too quickly and it's too small. You just can't see it. But using the data, we can come up with pretty good ideas of how reactions proceed. You would have to know a little bit more about bonding patterns and how different bonds are formed, what kind of intermediates might be formed. But at the end of the day, this is how chemists would get these mechanisms. They're not just pulling them out of their rear ends. The last thing I wanted to talk about before we finish the unit is just the graphical interpretation of rate laws. I want you to think about what those orders mean. So if you have a graph that looks like this is just kind of a sketch in your notes, but let's go through the different orders of a reaction. So let's start off with zero order. If you have a zero order reactant, it has zero effect on the rate. And a zero order reactant would look like this if you were graphing it. This would be zero order. Now let's think about why. Well, it doesn't matter what you put to the power of 0. I'm just going to put a to the power of 0. It doesn't matter what number goes in a's place there, your answer is always going to be 1. So your rate's not going to change, which is why there's no slope here. But if we're talking about first order gives us a linear graph. You're thinking about like y equals mx plus b. X has no power on it. It's just x to the power of 1, I guess. So this would be the concentration of a to the power of 1. So it's going to increase steadily. If you double it, it doubles, triple, triple, quadruple, quadruple, and so on and so forth. But when we get to this type of curve here, now we're talking, second order. And if you think about in math, you guys have graphed y equals x squared. Well, you get a parabola, a curve shape. So this is second order, or a squared. This is where you're getting exponential growth. And if we make it third order, it's going to be the same thing. It's just going to be even steeper. And if you think about your graphing y equals x cubed in math, well, it looks like this. Well, we're only dealing with the positive values because you can't have negative concentrations. So this is what your graphs would look like if we're talking about rate versus concentration. And that's what we're trying to show. Zero order is flat, not affecting rate. First order is a steady increase. Second order is an increasing increase, if that makes sense. And a third order is an even more increasing increase. So that's basically showing exponential growth. And that should be the end of our kinetics unit.